first one is related to quantum computing, and second one is related to QKD, quantum key distribution. so, so quantum computing. So here we are developing a FPGA-based solution for the superconducting based quantum computer. So in which we are generating some RF pulses. So those RF pulses will be provided to quantum fridge. So after that, it passes through the quantum fridge. We'll receive those pulses back through ADCs. So this is the evolution board which is having inbuilt DACs and ADCs. So we can generate signals through DAC, and we can receive the signals through ADC. Whatever the signal will generate and whatever that signal data will receive, we have to compare that data, and from that we can measure the state of the qubit. So let's say we are generating this modulated sinusoidal wave. So there are three parameters for the signal mainly. So first one is phase, frequency and amplitude. So like we can generate two signals, I and Q, which will be having phase difference of 90 degrees Celsius. And if you manipulate the phase, then whatever data we have received, so by plotting the data in the IQ plot, so we can measure the state of the qubit. So in that we have to repeat the number of iterations, so like 500 times, 1000 times, and in that we can verify that whether that that gate is applied or not on that specific qubit. Let's say NOT gate or CNOT gate or Hadamard gate. So in that way we can verify that. Yeah, so right now, sir, the solution is developed for single qubit. So single qubit, let's say.
This entire board is for single qubit.
Yes, sir.
So if you have to have a multiple qubits, so can you have the similar replication?
Yes, sir. So in this board currently there are 8 DACs and 8 ADCs. So let's say for a single qubit we need 2 channels.
Right.
So considering that, so this board supports up to 4 qubits. So if you 4 qubits the board supports. You can control 4 qubits with this evolution board. And if you want to let's say expand this solution for multiple qubits, then you can stack such boards. So by giving external clock, so we can synchronize all the boards using external clock, and we can operate 8 qubits, like 16 qubits. So in that way you can work. Yeah.
What is full stack? Some full stack they use. What is
Yes, sir. Let's say so this single board can be used for 4 qubits. So if we take such two boards, and if we provide synchronous clock, like single clock to both the boards.
okay? Is it possible?
Yes, sir, it is possible. So there is a provision of external clock in this FPGA board. So basically this is the UltraScale Plus board from Xilinx. So it has inbuilt data converters. Then this processing system is there. So this application processor is there, ARM Cortex A53, and one real-time processor is there, R5.
What is cooling requirement for that?
Huh?
Cooling requirement.
Yes, sir. Actually, for this board, no cooling, external cooling requirement is there. So this fan is there, so that is enough. So below that fan, RF SoC is there. It's fine. Yeah, yeah. And sir, the
Where you are computing it needs around 166 Kelvin and
yes, sir. So at IIC, so yeah. So physics, So physics laboratory is there. So there that temperature, that whole setup is there. So there that cylinder is there. So to simulate the qubit. So there they have realized the qubit in the cylinder. So there different temperature ranges are there. So like it goes up to 0 Kelvin, I think.
0 is anyway impossible.
Yeah. So whatever that, so like very low levels of temperature they go.
Yeah.
And
166 for quantum computing.
so 166 Kelvin, right? Yeah. So in that way they do that. Yeah.
For us, it is 166 is very low temperature. Coldest place, 94. Coldest place.
Yes, sir. And sir, this is regarding this quantum communication, QKD. So
This is the area actually. Encryption, now suppose this computer comes to know.
sir,
The whole our password
yeah.
technology will go for.
Yes, sir. So any more questions about this you can ask. So yes, sir. So this is regarding this quantum key distribution. So
Yes.
yeah. So basically there are two parts, Alice and Bob, and there is in between some Eve is there. So who tries to steal your key. So here basically, so this first pulse, it is regarding this quantum communication part, and the second one is the clock, and third one is the gate signal. Yeah. So basically, what demonstration we are giving is we have to detect the photon, so which is coming from the Alice side. So So in order to detect that photon, so we shift this gate pulse. So photon means it is coming in the form of some gate pulses, and this gate pulse we have to shift in a such way that they will overlap. So when that overlap, when that photon pulse and this pulse will overlap, then that the SPD will detect the photon, single photon detector. It will detect the photon, it will generate NIM pulse. That NIM pulse will be given to time to digital converter. Then it will generate a trigger of timestamp. So let's say some 16-bit or 32-bit. The same timestamp will be generated at Alice side, and they are exchanging this keys by using this timestamps. So at what timestamp what data is received. So they'll match these timestamps, and then they can decode the data. So in this way the communication happens.